All right, in this video, we're going to continue talking about section 11.3. This is part 2. So we're going to continue talking about tangent lines to curves. And so here we just have another example of us finding the tangent line to a graph. And so once again, in order to do that, we know to write the equation of any line, we need a point and a slope. And so the point is easy to come by. We know it's going to be happening at -1, comma. And then, of course, I need to find f of -1, which is going to give me -1 squared plus 2 times -1 plus 3, which is going to be -1 minus 2 plus 3, which, of course, is 0. So we know we have the point -1, 0. What we now need is we need our slope. And our slope is going to be found by finding the derivative of the function at -1. I suspect I'll need a little more room here. Okay, so I need to find the derivative of f of x at the point -1, or at the location -1. So I'm going to do the limit as x approaches -1 of the function -x squared plus 2x plus 3 minus the value of the function at -1, which we just calculated to be 0. That's why it's kind of handy to do that first so that you don't have to do it now. All right, and then we're dividing by, of course, x minus, and we're approaching -1. That's the location. Okay, so let's clean this up. The limit as x approaches -1 is -x squared plus 2x plus 3 over x plus 1. I want a factor, but before I do that, I'm going to pull out the -1, giving me x squared minus 2x minus 3 over x plus 1. And hopefully, when I factor this, it will have a helpful factor that will cancel out. So I have x, 3, and 1, -3, +1, and sure enough, x plus 1 cancels out, leaving me with the limit as x approaches -1 of -x minus 3. So now I'm going to evaluate that limit. Don't like that I ran out of space, but I have found the derivative at -1 is equal to, evaluate the limit, I get -4 makes +4. And so my slope is 4. So then I have y minus 0 equals 4 times x plus 1, or y equals 4x plus 4. That is really ugly. Let's fix that. Okay, now let's graph the above scenario. So let me turn the graph paper on. Let me get smaller paper. All right, so we're going to graph the function. And what are we graphing? We're graphing y equals -x squared plus 2x plus 3. Just because we need the practice, I'm going to put this in vertex form so I can graph it easy. Factor out a -1 out of x squared plus 2x. I'll leave the 3 as +3 outside the parentheses. Half of 2 is 1. 1 squared is +1. I have added 1, but not really. I really actually subtracted 1. So that means I need to add 1. So this is going to equal -1 times x plus 1 squared plus 4. So my vertex is at -1, 1, 2, 3, 4. Something's wrong because I have the point -1, 0. So let me check my mistake here. Let's see. There it is. And I factored out a -1, but I did not change my -2x. And the only thing that's going to change is that's a -1 right there, which is nice because now I actually know the vertex is at 1, 1, 2, 3, 4. And let's change colors. So it's upside down with the typical pattern. So I'm going to go down 1, go down 3, go down 1, 2, 3, 4, 5, match it on the other side. And I have a parabola that looks like this. All right, I have asked you to find the tangent line. And so we know it's going to pass through this point right here. And the slope is 4. So 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. And I get a line. Looks like this. Obviously, the picture graph is not perfect, but certainly that appears to be in the realm of correctness. Okay. Let's keep going. Also, we know it's correct because I started here and I did hit my y-intercept, which is what the line says. All right, moving on. Example 4. Example 4 is interesting. Let's kind of preview it before we get too far. So find the derivative of this function at -2. Find the derivative of the function at -1, at 0, at a half, at 3. I'm super lazy. I don't want to do that because unfortunately what I'm going to end up doing is the same work over and over and over and over again. So instead, what we're going to do is we're going to sort of just jump ahead and preview what's known as the general form of a derivative. All right, so we're going to talk about the general form of derivative. And in order to do that, we're going to kind of go back to our picture. And we're going to kind of make an arbitrary function. And let's review kind of how we set this up before. When we were doing this before, we talked about, let's find a specific spot. So we said, let's talk about this value here at A. So we set this up and we said this then would be the point A, comma, f of A. And then we said, let's pick another point. Let's call it X, which would make this point right here, X, comma, f of X. And then we said the limit as X gets closer to A. So we're going to pick this point of X, which is maybe this far away, and then we're going to move it closer and closer and closer and closer. So we're going to move X closer to A, all the while taking the slope as we do it. So the slope is f of X minus f of A over X minus A, and this was the definition of the derivative at a specific point. That's a little messy. I don't like it. I'm going to fix it. I'm going to move this right here. So the derivative of the function at A is found like this. Okay, so now I want to make a little change. So I'm going to come back here and kind of reset this picture. So I'm going to go again. So this time, I'm going to draw my curve, same basic curve. And instead of pick a specific point of A, like here, A is a specific number. It's not a variable like this is a variable, X is the variable, A is an arbitrary constant. So instead of doing that, let's start this way. Let's go ahead and pick a value. And let's say we're here at X, where X is not an arbitrary constant anymore. X could be any value that we want in the domain. And so therefore we have this point right here, which is at the point X, comma, f of X. All right. then instead of pick another point like we did before, we're going to instead pick the same concept. We're going to come out this far to here, but instead of name this point, I'm going to instead name the distance that we traveled h. So now, instead of having 2 points like we did before, we have 2 points. One of them is at x f of x, and the other one is right here, which would be this x value right here would be a distance of x plus h, making this point then x plus h, comma, f of x plus h. So then if I found the slope, gonna need some room here. If I work on finding the slope of this, so we connect the secant line, and now we're going to do the same thing. We're going to find the slope of that secant line is equal to the y value, f of x plus h, minus f of x, y minus y, over x minus x, so x plus h minus x. And so then the secant line becomes f of x plus h minus f of x, and then the x's cancel and I get h. And it should make sense that we're down to h in the bottom, because finding the slope, it's how far horizontally did we change. And we defined that by the value of h, so it makes sense that our horizontal change is h. This, of course, we recognize as the thing called the difference quotient. So now if I want to make this the tangent line instead of the secant line, what do? The slope of the tangent line just means I need to bring the points closer together, just like before. So now I'm going to take the limit, and what's the distance between them? It's h. So instead of bringing the points together, I'm going to bring the distance between them down to nothing. And so now I have this statement right here. This right here is what's known as the general form of a derivative. So what does this do for us? Well, notice what it doesn't have. It doesn't have a specific value we're finding the derivative at. What this finds is just in general, no matter what x is, this is going to give you the way to find the derivative. So why would we use this? Let's back up here. In order to take the derivative of all these points, we have to do the same work repetitively as we're simplifying the limit, right? As we've shown in the previous video and up above. Like, we know the math to do to simplify and find a limit. So I'd have to do that over and over and over and over again. So let's now take a look at what happens if we find the general form. So I'm going to take the derivative of the function, and now I'm going to use my new general form. So the limit as h goes to 0 of f of x plus h minus f of x over h. So the derivative, and again, I don't care about the point yet. I'm just going to evaluate this as it's said. So f of x plus h would mean we plug in x plus h squared minus f of x is x squared over h. Take the limit as h goes to 0, would be x squared plus 2xh plus h squared minus x squared over h. The limit as h goes to 0. Let's see, the x squareds cancel out. I get 2xh plus h squared over h. I'm going to factor h out. Oh, yep. And of course, those cancel. Which brings me to the limit as h approaches 0 of 2x plus h, which I'm now going to evaluate, right? F prime of x. And so f prime of x equals evaluate h going to 0, and I get 2x. This is what I would call the derivative of f of x, which happens to be x squared. So the derivative of x squared is 2x. Now, what does that mean? Well, what we've just created is we've done the exact same math as before, but this time where we're taking the derivative is irrelevant. We're taking the derivative somewhere, some x value. And so I've created this function, which is the derivative, which is based upon solely what the x value is. So now, if I want to find the derivative at -2, then I know that the answer is going to simply be 2 times -2, because x, right, the derivative of -2. So I'm replacing x with where I'm taking the derivative at, and I get -4. And then I can take the derivative at -1, and I get -2. And I can take the derivative of 0, and we get 0. And a half, we get 1. And 3, we get 6. And if you compare those to the ones we did back in video number 1, where we found, I think, 4 of those 5, you'll see that they all match. So what's the benefit here? The benefit is if you're going to be taking a derivative of the same function multiple times, we don't have to repeat all the work. We find the general form of the derivative, which then we can use for any x value. So what the derivative simply is in this simplified version is we've created what I would call a slope generating function. And now I just need to know, where do you want to know the slope? I plug in that x value and it tells you. Okay? So hopefully that makes perfect sense. If it doesn't, go back and kind of watch this again or come talk to me. Let's keep moving on. All right, find the general form, the general derivative of f of x equals x cubed. So that's just going to be us, once again, finding the limit as h goes to 0 of our difference quotient. This would be the derivative of f of x. So in our case, we're going to have a limit as h goes to 0 of x plus h cubed minus x cubed over h. All right, equals the limit as h goes to 0. Now, I'm going to keep my work pretty clean right here. And x plus h cubed takes a little bit of doing, whether or not you're using the binomial expansion or just mathing it out. Either way, you got a little bit of work to show. So I think I'm going to do that off to the side. So I'm just going to do x plus h cubed, we know is going to be x plus h times x squared plus 2xh plus h squared. And then I've got to distribute and do one more. So x cubed plus 2x squared h plus xh squared. And then h times x squared is going to be another x squared h, and then 2xh squared, and then h cubed. So x cubed plus 3x squared h plus 3xh squared plus h cubed. Binomial expansion, we should go from a 3, a 2, a 1, and a 0 x's, h's, 3, 2, 1, 0 h's, working backwards. And then we're on the third row, so it's 1, 3, 3, 1. Right, so whatever your preference is, x plus h cubed, I don't mind doing that one by hand. Probably about equal time for me to be confident in my binomial expansion answer. Okay, but let's get back to the problem. I'm going to take that over here. So I get x cubed plus 3x squared h plus 3xh squared plus h cubed. Minus x cubed. Almost forgot the second part of that numerator. All over h. All right, we cross off that. If everything has gone as planned, then we should have only things with h's left. And I'm going to save myself a little space. I'm going to factor the h out as I go here. So I get 3x squared plus 3xh plus h squared over h, which cancels. Limit as h goes to 0 of 3x squared plus 3xh plus h squared. All right, it's now time to take the actual limit. Let's let h go to 0, and I get the derivative of the function is equal to this goes to 0, this goes to 0, and I'm left with 3x squared. So what does that do for me? If I'm looking at the graph of x cubed, which we know looks like this, now if I want to find the slope, say, at 0, I just plug in 0 for x and I get 0. If I plug in 1 and I want to know the slope at 1 squared, I get a slope of 3. If I do a slope of -1, at -1, then that's also 3. Notice that no matter how we look at this or where we look at this, whatever point we use, the tangent line, if I kind of slide that line along here, which I can't really do digitally, my apologies, notice that it is always positive until it's 0 right here, and then it turns to positive again. Let's look at the math. It's x squared, meaning whatever x you plug in is going to be squared and turned to a positive, making every answer you get either positive or the one time it's 0. Okay, so this is the general form of the derivative. All right, so we're going to do that a couple more times. Looks like twice. So here we go. Ooh, I don't like writing in red. The derivative of the function is equal to the limit as break the habit as h goes to 0 of x plus h to the 4th plus 18 minus x to the 4th plus 18. So we can already see those 18s are going to cancel out. All of this, of course, over h. Okay, once again, I'm going to do this work over here. So I've got to figure out what x plus h to the 4th is. This time I will use binomial expansion. So I know it's going to be x to the 4th, h to the 0. I know it's going to be x to the 3rd, h to the 1st, x squared, h squared, x first, h cubed, and then of course it'll be no x's and h to the 4th. What are my values, my coefficients? We know we have 1 and we have 1. We know we're at 4 and 4. And if you're like me and you're like, gosh darn it, what is the next number in the middle? I don't remember. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. It's a 6. I think that'll be faster than multiplying it all out. All right, let's bring it over, clean it up. I'm going to have x to the 4th. I'm going to have plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th plus 18 minus x to the 4th minus 18. Lim as h goes to 0. All right, x to the 4ths cancel. Negative 18 and plus 18 cancel. And let's bring it down. And I'm going to again save a step. I'm going to factor h out as I go, hopefully not making an error. Giving me 4x cubed plus 6x squared. One of the h's is gone. Plus 4x, one of the h's is gone. Plus h cubed. H cancels. Limit as h goes to 0. 4x cubed plus 6x squared h plus 4x h squared plus h cubed. Now I can finally actually plug in 0, and so the derivative of the function at any value x is going to be equal to, this goes to 0, 0, 0. That leaves me with 4x cubed. There's my slope generating function for x to the 4th plus 18. Notice the plus 18 never played a role in the problem. Why is that? Well, if we take a look at this, we know that x to the 4th is some version of this. It's very parabolic looking. X to the 4th 18 is just the same parabola right here. So whatever the slope is at 0 is the slope of this one. The slope at 1 is going to be the slope at 1, right? So the 18 ended up not mattering because that doesn't impact the slope at all. So just interesting thing to point out. All right, let's do one more and then we're done. Okay, this one's a little bit different, not a polynomial. So let's find the derivative by doing what we do. Taking the limit as h goes to 0 of 3 over x plus h plus 2 minus, I almost put plus for some reason, minus the function. All over h. All right. So now we got to do some math. I plug in 0, and I have a problem that it's going to be 0 over 0. Always going to happen. So we need a plan, and I think my plan is a common denominator. So I'm going to multiply top and bottom here. And then over here, I'm going to multiply by x plus 2. So I'm going to get 3 times x plus 2 minus 3 times x plus h plus 2. I'm going to just go ahead and put those all over the common denominator we just created, which would be x plus 2 times x plus h plus 2, and of course all of that is over h. All right, got some algebra to do. Jump too far. Equals the limit as h goes to 0 of 3x plus 6 minus 3x minus 3h minus 6 over x plus 2 times x plus h plus 2. Hopefully everybody understands why I'm simplifying the top but not the denominator. Think about the answer to that and talk to me if you're unclear. All right, what happens here? My 3x's cancel. Oh, my 6's cancel. That leaves me with negative 3h over x plus 2 times x plus h plus 2 over h. Dividing with a fraction within a fraction, we know we're going to want to multiply by the reciprocal. I'm going to go ahead and just move that work up here. So I'm going to get the limit as h goes to 0 of negative 3h and then multiply by 1 over h. At this point, I can clearly see that my h on the denominator is going to cancel my h in the numerator, leaving me with the limit as h goes to 0 of negative 3 over x plus 2 x plus h plus 2. And now I can plug in an h of 0. And when I do that, I get the derivative of the function is equal to, plug in 0, I have negative 3 over x plus 2 x plus 2, or negative 3 over x plus 2 squared. All right, before we finish with this question, I think I'd like to look at it on a graph and make sure that what we've answered makes sense. Although my computer is really starting to misbehave. All right, what do we know about this graph? Come on. There we go. All right, I'm going to turn on graph paper again. We know that this is a graph of a rational function that has moved over to negative 2 and has an asymptote at negative 2. We have a horizontal asymptote at 0. And it's going to be your standard graph, but 3 times as tall. So that means instead of being over 1 at 1, I'm going to be over 1 at 1, 2, 3. And instead of being over, let's see, 1 and 1, so then I'm going to move over to 3. 3 over from that, and I should be at 1. And that would give me a graph that looks roughly like this. And matched on the other side. 2, 3, and 3, and graph. Okay. Now let's take a look without looking at our general form of derivative. Let's just think about the slopes of this thing. The slopes, and again, I really wish I could kind of easily kind of trace a line around this graph, but if we kind of start looking up here, then I have a slope that is negative, pretty steep negative. If I move here, I've got a slope that's negative, less steep, negative, less steep, negative, less steep, so less steep that really it's approaching 0 as a slope, right? As we keep going out there, it's going to look very horizontal, so obviously its tangent lines will be very horizontal or 0. If we kind of look over here at the slope over here, we've got very horizontal and a little bit negative, less, but still negative, less horizontal. Now we're heading to vertical. The closer we get to -2, the more vertical it should be. In other words, it should be like a negative, very, very, very big number. All right, let's take a look at our derivative. Notice, as we talked about that, the slope of every point is going to be negative. And look at the math here. As I plug in numbers, I'm going to square, divide, 3 divided by that, and then make it negative. So this does at least seem to describe that. We should be aware that there is no derivative at -2, because there is no point at -2 to find the tangent line 4. And I look here, -2 is undefined. So that tells me I can't take the derivative at -2, and that should make perfect sense why. And a couple last thoughts. As I let x get very, very large, like I go out to 100, we know that I should have a slope very close to 0. But if I plug in 100, I get an answer very close to 0. If I plug in a number very close to -2, like -1.9999999, then that's going to give me something in the denominator that's basically 0, right? I'm going to have 0.000001 squared. And then when I divide by 3, I'm actually going to get a very large number. And that is verified by the extreme slope as we get closer to -2. So this really appears to work. Okay, I hope everybody's good. This video probably went a little bit long. If you hung this long without fast forwarding, congratulations. Hopefully you are soon to be a derivative master. I'll see you in class.